want to smoke cannabis. Doctor say make a pop one of this. Make me fly like say I'm Aladdin. Come bring some kind melodies. Oh, mama, myself no do past like this. So many things inside of my jeans.
Julio?
Start down, DBTs.
Okay.
Hello.
Okay. So we'll resume. Thank you to have a seat. Okay, thank you. We are slightly late, but it's what time is it? Yeah, not to 10 minutes, even not 6 minutes late. Okay, thank you. So we will resume our meeting with a session on new renewable energy sources and new technologies regarding first natural hydrogen as a renewable energy sources and new devices for photovoltaic cells. And after we will have two projects on recycling of renewable energy equipment and one on modeling also. So the first project is called HyAfrica. It's dealing with natural hydrogen as a resource. Julio Carneiro is online. He was supposed to be there on site, but unfortunately, at the last moment, he could not achieve. So, Julio, if you have your microphone open, you have the floor for 20 minutes, and after we'll have 10 minutes question. The floor is yours.
Hello, good afternoon. Can you hear me? Can you see the presentation? Not yet. Hello?
We can see the presentation.
So good afternoon, everyone. Sorry for not being on site. Tested positive for COVID at the very last moment to travel to Rwanda. I thought it was really stupid to travel. So, unlike it is. So, this project is, as Francois was saying, quite different from what we've been seeing in this morning. It's more related to quantifying resources, natural resources, in this case, hydrogen that is produced directly from nature. I did not prepare a technical presentation. I did a technical presentation yesterday at one of the thematic sessions, and this presentation is more about the progress of the report, both in terms of the results that we were supposed to achieve, but also some of the challenges that we are facing. We just turned 1 year because we started late in August 2022. In fact, some of our partners only signed contract already in 2023. That is part of the challenges we face. This is the consortium. So it's led by Converge, which is a Portuguese SME. It has two research institutes from Germany, Leibniz Institute for Applied Geophysics and Fraunhofer. And it has 5 universities, one from Morocco, University of Mohamed Premier, University Eduardo Mondlane from Mozambique, University of Pretoria, and the University of Limpopo from South Africa, and from Togo, the University of Loma. We also have one governmental regulatory body from Mozambique, the National Director for Geology and Mining, and they are expected to have a key role in one of the objectives of the project. So essentially the main goal is to map the existing resources of natural hydrogen in 4 countries, Morocco, Mozambique, South Africa, and Togo. But not only that, it's also to understand how can they be applied in standalone energy systems and in off-grid systems for isolated communities. That's why we are more related to Mark III and Mark IV, because it's a local source of energy, well, at least that we expect has the capacity to be applied for energy supply to small communities, as it is done nowadays in the only project in the world that is utilizing hydrogen, natural hydrogen for energy supply in Borakibugu in Mali. So, what are our specific objectives then? We want to identify and map the existing resources, already said that, but very importantly, and this first specific objective has mostly to do with earth sciences research. But from that on those first specific objective, we want to assess its socio-economic impact and to understand what business models can be used for supplying energy from natural hydrogen. And then we want to engage with the stakeholders and policymakers in each of these 4 countries so that they can develop roadmaps and action plans for systematic exploration and hopefully exploitation of natural hydrogen, because we're not assessing the 4 countries that would not be feasible within the 3 years of the project or the resources we have. We are focusing in very specific, which we think are highly promising regions in each of the countries. After that, we want, or we expect each of the countries to develop their own strategy. But because also natural hydrogen is so poorly known, or at least it was until 1 or 2 years ago when it submitted a proposal, nowadays there are quite a few teams around the world already working on it, sometimes at a commercial scale. Anyway, we wanted to build capacity about it within the consortium. That's our African partners think about and have previous knowledge about natural hydrogen. Sorry, that's a noise. I'll excuse myself. There's no, okay, stop. Sorry, problems of being at home. And we're engaging with them. Just very briefly, what is the structure of our project? The three work packages at the top are essentially their science projects. That's where we assess the existing resources. That's ongoing. That's what we've been doing most, together with the building capacity in work package 6. The 2 at the bottom are essentially developing the roadmap, so interacting with the stakeholders and policymakers, and socioeconomic impacts, and that started last month according to schedule, so no delays there. That part is going very well. Each of the local teams has the responsibility to characterize their own resources and engage with the stakeholders, because they have the knowledge not only about the geology and geophysics of the area, but also they know the stakeholders, which obviously the European partners do. So first results. So I presented a more detailed part of this yesterday, but we did find, according to what we expected, several natural hydrogen sites in our target areas. We used the remote sensing initially, then went into the field, did some field measurements of hydrogen concentration, and we also interpreted the geological and geophysical information to build models to understand what are the sources of that hydrogen. And in the first year, and I'll come back to this later, only in 2 of the regions, we had works in 2 of the target areas in Morocco, where we found very interesting hydrogen seeps up to 500 ppm. What you see here in the figure below is one of those hydrogen seeps with a clearly indicating a structure where hydrogen is venting to the atmosphere. This is done at 1 meter depth, so it's clearly in this case up to 400 ppm. But you can see here clearly a hydrogen seep. We could identify, I won't go into details into this, so there's several hundreds of these structures there. We could identify, at least for the moment, we are convinced, we could even model in 3D what is the source of the hydrogen, and we quantified an estimated production in our target area of around 21.5 tons per day of hydrogen being produced. When I mean produced is by the natural reaction, in this case of water at depth of 5-6 kilometers depth, of a hydrogen reacting with the hydrogen-rich rocks in a process that geologists call serpentinization, in which these hydrogen-rich rocks, for instance, basalts, react with the hydrogen and produce other minerals, but also release hydrogen. Of course, this is a first estimate of the production. It does not mean it is what it is the amount that is available for capturing, because this is the production, but then there needs to be a cap rock, an accumulation of hydrogen. We are working on that. And we also did the same flow, the same workflow for the South African target. You see here, these are known, these small lakes or depressions are known in South African spans. We are very much convinced they are related to hydrogen sips, and you can see here that according to a profile, as we get close to these structures which are flooded, so the measurements, the hydrogen concentrations start to increase up to 2000 ppm. In this case, just to remind you that the natural the expected concentration of hydrogen is 0.5 ppm in nature. So really, we have high values. But more interesting than that, in South Africa, we get to values above 10,000 ppm, so about 1% of hydrogen at 1 to 2 meters depth, which is really a strong anomaly. Nevertheless, and though the potential is higher in South Africa, at least with these first results, we understand less about what is the source of the CO2 in South Africa. It does not seem to be that serpentinization mechanism that I just spoke about. So we did this. What we also did was to did some 3D modeling. In this case, is for utilizing the geophysical data. We did the the 3D modeling of the iron-rich rocks, which could be the source of the hydrogen in depth, which are these bodies here, these dark bodies here that you see within our study area. They seem to correlate quite well with the hydrogen production that we see in Morocco. And so we are going to do, this is one for survey. We are scheduling it up in the north. Was up here in the north. We are scheduling a different news field survey because we detected a high iron-rich body in the south, and we want to do test if hydrogen is also occurring. In South Africa, this image here just illustrates how well the hydrogen structures, which are these red lines, are controlled and oriented according to the main fractures and faults, which gives some hints about the possible behavior of hydrogen in depth. So it is pretty much controlled by faults. It's not related to the same iron-rich body, so we are looking at other potential sources for hydrogen. Natural radiolysis, metal degassing, there's a whole range of them. And we have to look and try to understand what are the source, because if we understand what is the source, we then know where to look better for the highest concentrations. So this is in terms of the technical results, very briefly, but also it is important. We put a lot of relevance to the building capacity and raising awareness. Right at the beginning of the project, we assembled a group of external experts on natural hydrogen, Air Liquide, United States Geological Survey, University Grenelle Alpha, European Federation of Geologists, and Natural Hydrogen Energy, which is a company. And we did a workshop for the African partners in the consortium, just kind of kick off knowledge about them. Well, to do a state of the art of the technology. We then also conducted training of the local teams in Morocco and South Africa for the field service. They are now autonomous, they do it on their own now. They have also acquired the equipment for that. And last month, together with our General Assembly in Pretoria, we also organized the first workshop in Work Package 5 about raising awareness about natural hydrogen for South African stakeholders involving public and private institutions, academia, research, mining. and energy, and it was very interesting. This is the kind of topic that we discussed. There was a panel at the end where we discussed. Well, actually, South Africa has a very ambitious hydrogen strategy, not natural hydrogen, but green hydrogen strategy, and we were discussing during this first workshop if and how could natural hydrogen be in that ambitious green hydrogen strategy as a complement, not to complement to the green hydrogen. It's not feasible with the known resources to think about replacing green hydrogen by micro. That to be a complement. Okay. There has been some visibility of the project more than we expected at the beginning. There were several contacts since we launched the project from industrial companies trying to inquire about the results, and some of them actually offering to cooperate with Africa. In some cases, quite large companies like Engie being interested in the result and seeing opportunities in the future. The Moroccan National Oil and Mining Company was very keen on participating in our field survey in Morocco. So they were there with that information. They were very good help. GTEC is an English geophysical company. They provided a lot of geophysical information for the Mozambique and Moroccan existing information, which is expensive anyway to buy, but they provided, as long as we showed them their own results about the geophysical interpretation with them. That was good. They also asked to join the consortium, but that was not was adequate at the moment. The Hydrocarbon Authority in Mozambique also inquired about the project. I had a meeting with them. They might be interested in joining the consortium. Since they are not a private company, we might consider it that it's possible. And of course, we'll have to check with Luke. We were contacted by the advisors from Hydrogen Europe to do a similar project for the Sahel countries. Well, it's not the most safe countries, but it's an area to field work at the moment. And there was a few very relevant. There were a couple of interviews in the Spiegel and the Standard journals with our Germany colleagues, and then following from that, we were contacted by the TV channels EDF and a producer from CNN Africa. They wanted to join us in the field, and we actually, we haven't decided that is at this stage. We participated in the Mozambique Energy and Industry Summit. They invited us in Maputo, and there was a piece about us in a very popular science YouTube channel, Breaking Lab in Germany. So that was nice. Possible evolutions of the VHX in progress of the report. Well, the results, clearly the results in South Africa are already relevant enough to justify advancing more into actually finding sweet spots for exploitation in natural hydrogen. That is something that was not included in the initial work program, and it is not included because it would involve a lot more effort in work package 2 and work package. So 1 and 2, and to probably engage with the industry. Expensive physical exploration methods in work package 3. So it's not quite within the scope of what we can do in this project with the funding we have, but surely the results are already interesting enough to think about that at this stage. Problems encountered during the project. Well, the due diligence that was requested from the 2 Mozambican partners, the University of Guatemala and the National Directorate for Geology and Mining, is clearly just inadequate for research project. That took a lot of time for them to feel that. They signed contracts in 2022. One of them is still to receive the first funding. They still have no funding at all. And we have, and obviously because going into the field, that's where we do most of our expenses, and local teams need to have the funds. So we've been delaying the field work in Mozambique until they get the funds. Now it is scheduled for November 2023. So next month, I'm trying to go there, but if we can't, for some reason, it will have to be postponed again for April, because then we get into the rainy season and we cannot do the field works. We're kind of hoping that the situation with the funding is solved quite quickly. Sorry, am I running out of time? I'm not listening to you. Okay, I suppose I'm running out of time. So lack of funding for the University of Lomé is also a constraint, because they have the same problem. They have no funds. We didn't change the expected project results, although clearly they will be more focused on Morocco and South Africa than we were considering at the beginning. We left the option of these 4 countries to select 2 with the highest potential. As the works are going, we're clearly going to focus on Morocco and South Africa. So I think I have to speed up. We did not change the expected outcomes. At least we hope that by after if the project is successful, at least 2 regions will implement natural hydrogen exploration and utilization programs, increase their shares of renewables by using natural hydrogen, and have clearly set up business models for standalone systems. Main risks, this is the last slide, so I think main risks is the inability to solve the problems in Mozambique, especially. What are our main interests as consortium members for participating in Lipari clustering activities? We are very much interested in cooperating in any other project involving hydrogen strategies. But we also like to share with you data on socioeconomic conditions, energy demand, energy supply. This is very relevant for the work to be done in our work package 4 and work package 5, which started last month. So some of you might already have information about this, and that will be relevant to us. And sorry for taking too long. I suppose I took too long. Sorry. Thank you. I do not have sound.
Thank you, Julio, for this presentation of HyAfrica. So I will look in the room if there is questions. The microphone. Yes? We are looking for. So, Labed? Ask for a question. So sorry, Labed. There was the first question from Jean-Pierre.
Okay. Thank you very much for this interesting presentation. Okay, this question is important. As far as I understand, you had to make an evaluation of all the hydrogen resources, so to speak, in the world. As far as I remember, you did not mention at my knowledge, the only project which exists where you have a production of hydrogen, which is in Mali, where you have a small hydrogen production, which is feeding a small power plant, which is about, I don't know, a few 10 or 100 kilowatt, but no more. So this is my first question. Of course, your project is not to deal with the development and the production and the use of natural hydrogen. However, it will be interesting and I would like to have your comment on, do you feel that some of the so-called, I will not call them fields, of course, but some sources of hydrogen you have identified could be developed and could develop more or less in an economical way, if not now, at least in the future? Thank you.
So yeah, about the Mali project, I did mention it just in passing, but and our project did not require, obviously, that we go into detail in describing each of the project. Right, but we did include that in our workshops initially, about raising awareness and for building the business. So yeah, we are aware about the Mali case. In a way, it is the inspiration for our project, because unlike some other research teams that consider that natural hydrogen could be a large-scale energy source, we kind of more focus on small-scale standalone systems, pretty much like exist. As for the sources that we already identified, well, we are identifying them at the surface, which means that, it is hydrogen that is went into the atmosphere. It is escaping. That's not where we wanted to explore it. We want to find where it is accumulating. This is the first stage to understand where the hydrogen is being produced. Next stage, we have to understand if and where it is accumulated in the same areas. We need not only a source rock, but also some kind of trap, some kind of seed that lets it accumulate. That is part of the work that work package 1 to 3 has to do in the remainder of the project. And then to understand if it is economically feasible, we're starting working on that. And it will pretty much depend not only on the concentrations that we find, on the volumes that we find, but also on the local conditions and the needs of energy for the local communities. So it's not, I would like to say to you immediately, yes, we have a case to go out there and drill wells and start producing natural hydrogen. No, we're not at this stage yet. Signals, particularly in South Africa, very, very good, but we are assessing, it's a preliminary assessment. We are not at this project trying to drill and to produce hydrogen.
Yes,
Thank you.
Okay, thank you. Second question from Labed.
Well, thanks a lot for your presentation. Maybe we should clarify one thing also for the audience, that natural hydrogen does not exist in nature. It has to be made by splitting water. And you are referring to some hydrogen trapped in some geological reservoirs, as I suppose. And what I understood that your estimation is based on indirect measurements. You can correct me if I'm wrong, by remote sensing or by other geophysical methods. Sorry. So the first question, how precise, I mean, are these estimations when you come to map a region or a country or whatever the target is? And the second question, do you have any example of the exploitation of natural hydrogen in the world so far?
Yeah. Okay, so the first question. No, we use remote sensing at the very early stage, focusing on a region and try to identify where there might be a hydrogen SIPs, because hydrogen has some signature in terms of it causes some depression, some kind of pan, and some changes in the vegetation. So we use that as a first proxy to go out in the field and do measurements, because we are working at large areas. Even if we are in promising regions, it's still several hundred kilometers square. So we have to pinpoint what are the best locations. And then we go into the field and we measure the soil gas at about 1 meter depth with a probe and with hydrogen sensors and gas sensors, and we measure hydrogen. And you were right, up to a few years ago, it was considered that hydrogen as a gas did not exist in nature, but there's plenty of evidence not right now that they exist. And the best of all is just what the previous question just mentioned, the Mali project. Since 2012, they have a pilot project there. They are producing hydrogen. Hydrogen is not being is being used to provide electricity to Borakibugu, the small town where they are located. And the interesting thing is that despite it being run for 12 years now, pressures have not been declined, which goes in favor of a constant production of hydrogen due to reaction of water with rocks, either through natural radiolysis, that is the splitting of the water molecule by decay of uranium, thorium, and potassium in rocks, in minerals, or by serpentinization, the reaction with iron rich. So nowadays there's plenty of evidence about this, and there's several companies around the world that are starting to look at this and drilling wells very deep.
Julio, we have a last question for you.
Yes. Okay, just one question regarding the reservoir traps. I mean, if you have a natural reservoir trap, you will probably also have other gas species trapped there. Maybe sometimes hydrocarbons. How do you deal with that when you're exploiting the hydrogen?
Yeah, that's a very good question. That's a very good question. Usually, well, the Mali case would be the one everybody would like to find. They have 98% of hydrogen, pure hydrogen concentration. Yeah, that is, I don't expect to have that many cases around with such high concentration of hydrogen. So one of the issues that we are not looking into this project, but that some companies are looking at is how to purify hydrogen tends to occur in this kind of trap, probably with other gases associated with it. Sometimes gases that we also have an economic value, like helium, but in other cases with nitrogen, and that means purifying, and that all that comes into the balance of what might be the economic feasibility. Or methane. It can also, in some cases, occurs also with it has to do with in those cases with purification. That will have to cost. That's something we'll have to consider, not in technical terms, because we're not drilling that depth. We're not going to drill a 2 kilometers well, but trying to understand what would be the cost penalty if we need to purify hydrogen in any of the routes.
Yeah, I mean, linked to that also, I mean, and to the leakage of, in general, of gases to the atmosphere. I mean, hydrogen is a little bit less known, but molecular hydrogen does have a greenhouse gas impact. And of course, if it has other gas species in there, you also have to take into account the potential greenhouse gas impact of those. So my question is, have you evaluated that in terms of what you do post-extraction? How do you cap the wells? How do you treat, how would you treat, let's say, the leakage and the value chain of hydrogen after that in order to avoid the greenhouse gas impact that this can have?
Yeah,
thank you.
Those are very good questions. We could make another project, and a larger project around that. Hydrogen does have a small greenhouse gas impact. It is the hydrogen that it is leaking. Okay, the hydrogen that we're talking about here and that we measure is already leaking. It's already going into the atmosphere. Obviously, if we produce hydrogen from an underground reservoir and you utilize it, then you would also have some additional leakage that could occur, for instance, in wells or in pipelines or during its utilization. If you look, however, at what are the hydrogen, green hydrogen and blue hydrogen strategies around the world in terms of the amounts of hydrogen that is to be produced and utilized, I doubt that the impact that natural hydrogen could have on possible leaks of hydrogen in the atmosphere. There is, however, a study that it was done, I think, an English university, sorry, I can't remember now exactly which one, in 2010, they took estimate the hydrogen greenhouse gas effect, but it's not really, really high, but it does have some effect. Of course, all the other issues that we were saying about have to do with exploration, about the wells, how to explore it, that is far beyond the line of the HyAfrica project. It has more to do with industrial exploration if we come to identify them in the research. We're not dealing with that in this project.
Okay, thank you.
But very interesting questions.
Yes, thank you, Julio, for this presentation and the discussion. Thank you. We'll go to the next project in this session. Now we'll address enhanced PV cells development. The project is called QDSOC. It will be presented by Raphael Schneider, who is inside. So welcome. So Rafael, you have
20
minutes presentation. Go ahead.
Okay. So I'm waiting for the slides. So thank you. So the QDSOC project started in May 2022, was expected to end in April 2025, but two partners had some problems related to the beginning of that project. So we would clearly appreciate 5 months extension for the South African and for the French partners. Next slide, please. So I am the project coordinator of QDSOC, and the partnership involves a Belgian partner, University of Liège, University of Lorraine with 2 labs, LRGP and IGL, Mohamed V University in Rabat, Mohamed VI Polytechnic University, and okay, thank you. And also University of Witwatersrand in South Africa. The aim of the project was to develop quantum dot sensitized solar cells using highly important heavy metal-free quantum dots. So quantum dots, for those who are not familiar, are semiconductor nanocrystals that have high potential for photovoltaic application. And these nanocrystals will be used as absorbing materials in the visible and in the near-infrared region for the optimal use of the solar spectrum. And next, we will have to engineer the interface between that nanocrystals. The slide changed too quickly. Thank you. We will have to optimize the interface between that nanocrystals and titania photoelectrode using wet and vacuum deposition processes. The relevance of that project to Mars is to find new material and better design photovoltaic cells to make more efficient solar panels and decrease their cost for generating clean and renewable energy. But also develop devices that will not only allow autonomous but also decarbonated production of electricity and thus ensure energy independence. Next slide, please. So briefly, how does a photovoltaic cell work? Completely on the right, that quantum dots and nanocrystals. Light will be absorbed by the nanocrystals, an electron promoted from the valence band, VBM, to the conduction band, CBM, and that electrons will flow first to porous titania, then to dense titania, and finally to fluorine-doped tin oxide, a conductive layer that will allow electricity to be produced. France and South Africa are involved in the engineering of that heavy metal-free quantum dots. University of Liège is involved in the engineering of that porous titania and also of that interface. Mohamed V and Mohamed VI University in Morocco are involved in the engineering of that dense titania layer. And with all that consortium, all the skills required for the development of new photovoltaic solar cells are required. Next slide, please. So the key challenge addressed by this project are development of heavy metal-free quantum dots. In France, copper, indium, zinc, selenide. In South Africa, cesium, tin halides with optimal electronic and optical properties. optimize the structure and the electronic properties of the dense titania layer via magnetron sputtering and the properties of that porous titania layer by weight-based templating strategies. Control the microstructure of the titania network in order to form continuous and highly condensed interpenetrating nanochannels, allowing to maximize QDs to titania charge injection and minimize recombination. And finally, establish the mechanism that will happen once these devices will be illuminated by solar light. The performance we would like to reach at the end of the project would be of photoconversion efficiency above 15%. This would be a real challenge for photovoltaic cells that do not contain any heavy metal like lead or cadmium. Next slide, please. So, first, the results of the French partner. Shubham Shishodia is the PhD student recruited in France for that project. He's working on that project this 1 year. Without entering in technical aspect, he developed a fast, reliable, and cheap method for producing copper, indium, zinc, selenide nanocrystals. Using microwave irradiation. He optimized precursor, ligand, pH, microwave pulse. And here you have typical spectra for that materials. On the left, absorption spectra, and you can see that most of the nanocrystals absorb light in the whole visible region up to the near infrared, but this must still be improved. And the photoluminescence emissions on the left shows that the emission of that nanocrystals can easily be tuned simply by varying, for example, the zinc and copper ratio. On the bottom, you can typically see a TEM image of the nanocrystals produced. These nanoparticles have an average size of approximately 2 nanometers and are well crystalline. Next slide, please. In France, we started to send nanocrystals to our Belgian partner that will associate QDs with that porous titania, but we cannot, of course, send all nanocrystals to Belgium. We must make a quick screening. And this is why, in collaboration with Thomas Gries from the IGL laboratory, we also deposited titania, unoptimized titania, on FTO, then deposed QDs, and you can clearly see here photocurrent measurements and resistivity measurements here, for example, that the assembly of QDs with titania generates more electron, and that electron will be used later for photovoltaic devices. But also on the left, thank you. The resistivity of the transfer is clearly simplified, much more easier when QDs are associated to titania. Next slide. So now for South Africa, for photovoltaic devices, cesium, lead halides, typically here, are of high potential for photovoltaic application, but usually it's cesium, lead halides that are used. And the project of the South African partner was to develop, to avoid the use of lead, to develop cesium tin halides, nanocrystals. And you can see on the right the typical structure, crystalline structure of that nanocrystals, where the dots A correspond to cesium, B to tin, and X to halogens. Next slide, please. The South African partner experienced some problems because tin is at the +2 oxidation state. tin is easily oxidized into tin plus 4. Vacancies are formed in the crystals due to that oxidation. That oxidation may also disrupt the crystal lattice. So the South African partner has to react quickly and find solution to that problems. Next slide, please. This is why in South Africa they have decided to dope that cesium tin halides with copper. And you can see here X-ray diffractions of that materials. The crystallinity is not altered after doping with copper. That materials maintain the classical crystalline structure. But what is also of interest for that copper doped materials, due to that doping, the band gap is reduced, indicating that copper doped copper tin halides will absorb more visible light than conventional crystals. But also at the bottom, you can also see photographs of that crystals, doped and undoped, and that copper-doped crystals exhibit a much higher stability, more than 1 month, compared to that undoped. Thank you. Next slide, please. So now for work package 2, the results of the Belgian partner that plan to develop porous titania layers. A templating strategy was used, typically deposition by spin coating of polystyrene beds at the surface of a conductive layer, stabilization, then infiltration of the titanium precursor, calcination, polystyrene is removed during that calcination, and you generate porous titania as indicated here. So a 2-step protocol. They also developed a 1-step protocol, mixing the titanium precursor on that polystyrene beds, and in 1 step obtain, after calcination, that porous titanium. Next slide, please. So I will not enter into many details. A few key points using that strategy. A highly porous titania layer with a specific surface of 124 square meter per centimeter per cube centimeter could be prepared. That layers are relatively thin compared to other methods, 0.7 or 1 micrometer, and this could still be improved. But the PV efficiency was evaluated not using quantum dots at present, but using organometallic complex containing ruthenium. And you can see the results here that are promising for both types of materials. The only small problem that we have at present is that the best results were obtained using that 2-step deposition, that it's slightly time-consuming, and maybe we could improve that part of the project. Now, from the result from Moroccan partner, typical, they are developing a new method for depositing dense titania layer, high power impulsed magneton sputtering, to deposit thin titania layers, a clean method, a fast method, that also avoids annealing treatments and high temperature heating to obtain crystalline titania. So I will not enter into the details of on that slide, but that method is called HyPIMS, and they have compared that process developed in Rabat to conventional magneton sputtering deposition methods. Next slide, please. So, once more, XRD diffraction patterns. Here are the dense titania layer prepared using that HyPIMS method. And on the left, titania prepared using conventional magneton sputtering. You can obviously see, if you compare both diffraction pattern, that titania prepared via HyPIMS is much more crystalline than titania prepared via conventional magneton sputtering. Peaks are much more well-defined. As indicated, titania prepared using the HyPIMS method, a mixture of two crystalline phases, anatase and rutyl, while only rutyl is obtained using that conventional magneton sputtering. All depends on the active spaces generated during the deposition process. Next slide, please. Typically, morphology of that titania layers, HyPIMS here, conventional magneton sputtering. You can see here at the top that dense films are obtained. They are also crack-free. And HyPIMS are denser than those prepared using conventional magneton sputtering. And the grain size is also reduced. Another important point that I obtained, next slide, please. They also evaluated the stoichiometry of that materials, and you can see here that for all films produced using HyPIMS, they are over-stoichiometric in oxygen, which is of high importance if you further consider the conductance of that titania layers. Next slide, please. Briefly, because that experiment only started at Liège, deposition of QDs at the surface of the titania layers, either dipping and infiltrations of QD or deposition via airbrush at the surface of titania. The first results are not optimal, are in fact modest, but the construction of that quantum dot sensitized solar cell will still be improved in the following months. Next slide, please. So, plan work, new pathway to explode. Depending on the results obtained after integration of that QDs in solar cells, both French and South African partner will explore new nanocrystals, if necessary, variation of the composition, shelling, surface ligand, modification of the quantum dot solar cell configuration, change the counter electrode. And at the end of the project, the Moroccan partner intends to develop a small prototype, 10 per 10 centimeter, to clearly demonstrate the viability of the results to be obtained in this project. The consortium is active. We exchange regularly for the work. We exchange also materials, and we all hope that the results that we will obtain during that project will allow us to continue the collaboration. At present, we have no new collaborations initiated, but based on the discussion that we had yesterday and this morning, I think that we may start to discuss with other projects maybe not only on photovoltaic photocell, but our materials may have other application in the future. At present, we didn't apply for any other project because we are only, let's say, 1 year and a half after the beginning of the project. Outcomes of the project, we expect to develop reliable standalone system architecture that can easily and widely be deployed in off-grid African rural and remote area, giving access to affordable energies to the largest numbers of beneficiaries, and integrate renewable energy into the global mix through versatile standalone system, and to help to address the energy needs of off-grid areas in Africa. Concerning the economic benefits, we have developed and demonstrated faster, less costly approach to develop and assess new materials for photovoltaic devices. We also expect to design photovoltaic cells to make more efficient solar panel and lower the cost of generating clean and renewable electricity. And finally, reduction of disposal and recycling related cost of the PV cells by the backward integration of the environmental regulation standards during the manufacturing stage. Next slide, please. Finally, we hope that the QDSOC project will contribute to strengthen African and European competitiveness in the materials science and engineering sectors, allowing for a rapid translation of results from laboratory and pilot test plants to the market, and such impacting different areas such as environmental, economic, social, and scientific communities. Final slide. Thank you for your attention and for your questions. There are many questions.
Okay. Thank you, Raphael, for this presentation. We will have now questions. I see Gundula, Bernardo. Yes. Gundula, so go ahead.
Thank you for this nice presentation. Should be on, no? Yeah. Okay. So I was wondering, because you are aiming at 15% efficiency?
Yes.
Yeah. And you said it's costly much more, so it's not so costly, so, but you didn't make any calculations, no?
I'm sorry, but I don't...
Did you make a calculation or on the costs? Because you said it's one of the benefits, because you just have the prototype.
Yes. A key point to start, we are developing solid-state quantum dot solar cells. All the labs are working on liquid with an electrolyte solar cells. And that liquid electrolyte solar cells are much more expensive than solid-state photovoltaic solar cells.
Yes, but I'm wondering when you compare it to standard PV crystalline cells, you know, you have an efficiency of 25%, let's say,
yes,
standard.
Yes.
For
silicon-based commercial are much close to 20 than 25.
Yes, okay, probably. But I would say a bit more, but anyhow, I was wondering about this cost benefit, you know, because when you compare it to standard PV and it's 15%, let's say, you need much more area, and you need much more time for installation, much more materials for installation, which is expensive. So I was wondering about this cost benefit compared to standard PV.
At present, we didn't evaluate fully the cost because we didn't develop that full photovoltaic for ourselves, but materials, titanium is cheap, copper is cheap, indium is less cheaper, I agree. But compared to other photovoltaic solar cells, the materials remain competitive. And processing that solar cells will not be a big problem, I think so. Even compared to silicon-based solar cells, silicon-based solar cells, you have to assemble N-doped silicon, P-doped silicon, and so on.
I mean, it's a proven product, no? So.
Okay. Thank you. Yes. Go ahead after Bernardo.
Okay, thank you for your presentation. Regarding the energy, the conversion efficiency of your PV cells, today or currently we have bifacial PV cells that can reach 21% of conversion efficiency. So, what is the main contribution in these PV cells in the market?
For my opinion, the first high interest is our PV cells will not contain any heavy metal. When you engineer solar cells, you have to think about the engineering of that solar cells and the end of life of that solar cells.
The
lifetime of that solar cells, they are not engineered, so I cannot say how long they will last. But there will be no problem for recovering the metals. They are of low toxicity. Metals should be easy to recover and hopefully to reuse in new PV cells.
And how your contribution or how your PV cells contribute to meet the actual PV manufacturing challenge, which is monopolized by China. What can be the contribution to this challenge, your product or your PV cells?
All will depend on the result that we will obtain. Of course, we have signed accord de consortium, consortium agreement. I hope that at the end of the project, we will be able to obtain one patent related to either the architecture of that solar cells or the new materials that we are developing for that solar cells, and that will help us to protect our results compared to solar cells prepared in China.
Raphael, we'll have a last question from Bernardo.
Thank you very much. So my question, I would have 1,000 questions. My question for you is, I know that the current efficiency record for quantum dot solar cells is around 18%, if I remember the latest NREL charts. The point here is, and it points a little bit to what the previous speakers have said, I think that you need to highlight very clearly what the competitive advantage would be of using these quantum dot solar cells versus the normal processes first, because it's not directly apparent. Okay, so that's the first one, and also compared to other thin film technologies and to the basic silicon PV cell, because in basic silicon PV cells, the use of heavy metals is limited. I do agree that there is a recycling problem, but I think you need to be very explicit on how your technology would address that recycling problem, and how is it different from other thin film technologies. In the end, the problem with any of these technologies is that you're trying to recover materials which have concentrations in the order of 10 to the minus 6. And that is not thermodynamically viable normally. So how does your proposal present an advantage respected to that? I do realize that you are at a very early stage in research. This is low TRL, so these are maybe questions for the future. Again, the other one is on toxicity, because toxicity of materials does not only have to do with the chemical species of them, but also on the, when you're getting to the nano-size materials, by their own structure, they can be disruptive to DNA material. You have the bad luck that I've been managing mostly PV projects for the past 10 years. So I've had to deal with guys that were doing quantum nanowires on top of silicon and stuff like that. And the main issue here is how have you considered the whole LCA of the cell, problems with leakage and encapsulation of the cell, and what would the cytotoxicity be of the material, of the nanomaterials that you release, irrespective of their composition, just because they are nanomaterials? Those are the two questions.
That materials have emerged approximately 10 years ago. That materials have emerged approximately 10 years ago, and numerous cytotoxicity studies were also already conducted. And it has been demonstrated that quantum dots containing copper, silver, indium, sulfide, or selenite are far less toxic. I don't want to say not toxic, but far less toxic than most ordinary crystals that contain cadmium, lead, or mercury. Okay.
Thank you. Maybe I have
une question au fond.
Yes, go ahead.
Okay, thank you. This is Gustavo de Miguel from the University of Córdoba. I want to thank you for the nice presentation. I think this is a good example to demonstrate that it's possible to do basic research in between two continents. So congratulations for this. And talking about a lot of disadvantages of these cells, I mean, there is a lot of things to do in the future. Toxicity is one example, yeah, but encapsulation is a solution, and it's going to be the solution. And replacement of the lead by tin is another solution. Of course, the problem of the stability, the lifetime, is an issue. We will solve it in the same way we have done with the silicon solar panel. Does anyone here know how to recycle the silicon solar panels? Nobody. And then we are going to use it. So they are not serious problems for this technology. We have to invest on this technology and, well, let the researchers do the things, and we will find a solution.
Thank you for your nice comments.
Thank you. Maybe
Yes.
I have a last. So no, you don't.
Just one last question. Well, regarding to your science, which is the most interesting theme for me at least, you try to enhance the lifetime of the tin perovskite by replacing tin with copper, right?
This was done by the South African partner.
Okay.
But that copper doping, in the slides I only mentioned copper doping, but other metals like silver, manganese were used for the doping.
And
that doping...
How did you know copper is replacing tin? What are the experimental...
It may not be only substitutional doping, it may also be trapping of that doping elements in the crystal lattice of the nanocrystals. It's not clear at present where the dopants are located.
And what is the change in the band gap of the material when doping the tin perovskite with copper? Because you said there was a decrease, an increase in the band gap. But
it's likely in our nanocrystals that we presented here, if you increase the amount of, for example, of copper, you will decrease the band gap and enhance the visible light absorption.
You are decreasing the band gap?
Yes.
By adding
decrease of
the
band
copper?
Gap. Decrease of band gap.
Decreasing?
Okay.
Yes.
Okay.
Okay,
thank you. Just I have maybe a last question from my part. If this kind of cell is developed and economically performant, does it will be specified for African market, or is it worldwide market?
From my opinion, 2 partners from Europe, 2 partners for Africa that sells...
No, but I mean the cell itself could be installed both. Yeah, will have the same performance in Africa and in the other part.
Of course.
There is no specific spectrum of...
No.
Okay.
No.
Thank you. Thank you very much.
Thank you.
So we will go now to the next project in the same category, if I may say, of enhanced solar cells, which is the project NANOSOLARCELL, which will be presented. I hope, by Conchi Anya, but I'm not sure she's online.
Not yet.
Not yet. Okay. Then we will split to the next project. So we will now quit the session on new renewable energy sources and technologies and go to a rather modeling project called OASES, which will be presented. I don't remember, but I know you are there. So it's your turn now. Thank you. Oh, it's SIREVIVAL before. Yep. Sorry, we had some change. So we will go back to OASES after this one, and we will address a project about second life and recycling of renewable energy equipment, mainly batteries. And the project is called SIREVIVAL. It's you. Okay. Sorry, I was not. Sorry. It's fine. Sorry, I didn't record. So you have the floor for.
Thank you very much. Yes, thank you very much. So we are not supposed to be at this time, but I'm the coordinator of the project SIREVIVAL. It stands for Silicon-Based Renewable Devices from End of Life Recycling to Revival of Photovoltaic Panels. And this project started last year, beginning of March. It will last till February 2025. It is not the same period for all the partners, and I'll give you more details shortly. Next slide, please. So I am the coordinator of this project. I'm coming from Université Catholique du Louvain, and we basically work here with partners from Algeria, Centre de recherche en technologie des semi-conducteurs pour l'énergétique, le CRTC. Then we have partners from France. It is the CNRS, the Institut d'électronique, de microélectronique et de nanotechnologie, le IEMN. And then we have two partners from Tunisia. These partners just started the project 6 months ago due to a financial constraint. So 1 year later, after the starting of the project. And they are École Nationale Supérieure d'Ingénieurs du Tunis, le ENSIT, and the Centre de Recherche et de Technologie de l'Énergie, le CREN. So basically, no, we didn't finish, but I just, you may be read. So basically, it's from the title. So the aim of the project is to reduce the environmental impact of the spent photovoltaic modules. And basically, we want to recover as many as possible materials from this silicon-based solar panels. Silicon is part of them. And then with that materials, we try to build new type of devices interesting for the sector. And here we have a peculiar focus on supercapacitor, solid-state capacitors, all solid-state capacitors. And then basically we want to continue the effort and to integrate these devices into new type of system. So basically our project will address two roadmaps. One, of course, is related to the recycling and second life of materials. And then, of course, if we go further with creating new products, we'll address this smart standalone systems to access energy in all its forms. And you pretty much understood that we'll cover quite an interdisciplinary area, starting from physics, engineering, chemistry, material sciences, and I'll give you some highlights of what we've been doing in the next minutes. So next slide, please. So our workflow is pretty much linear. So we're starting with recycling, as I said, well-defined products. We talk here about silicon-based solar panels. They can be crystalline or polycrystalline. And then we basically use this recovered material to upcycle them, and then we add new materials we create by our availabilities. And then we engineer new devices with these recycled materials, and then we try to reintegrate them and put them back into the loop. So basically, we have kind of technical objectives which we address. First is the efficiency of material recovery from this end-of-life photovoltaic panels. And we put there a threshold. I think we already have more than 90%, so I think we are doing pretty good in this aspect. Then we have type of materials that need to match this type of devices we want to build, and peculiarly we are interested in ionogels with large temperature operational windows, and here we already achieved this. We have ionogels, and I'll show you some highlights covering from minus 50 degrees Celsius to 100 degrees Celsius, and I think this is again an important achievement of the project. And basically we are now at the level to build this solid-state micro supercapacitor based on recycling material, because we already went into this recycling and now we are testing these devices. Then will come the integration of these devices in a new concept. So it's perfect. Yeah, you can change the slide. So as I mentioned, so I give here the first highlight of the recovery process. This process is done in Algeria by our Algerian partner. So let me tell you from the beginning, it's a specific system boundary I show you here, and if you want to hear more about this specific cut into the process, I'll present more in the thematic sessions, I mean, probably 1 hour after. And basically it's not an innovative process because, you know, technology is known about how to recycle solar panels. It's based on many manual processes, thermal processes, and chemical processes. But here are real numbers obtained in Africa by the African partners. And if you look carefully, basically the steps involve the aluminum recovery, the glass recovery, and then we recover the silicon and the silver, which are important elements that we'll upcycle in the process. So then, if you say, is this process competitive? I would say yes. If you compare with what is known in Europe from many European projects, you can take this famous FRELP process. It is documented in the reference you see there indicated at the bottom of the slides, and you'll have real numbers if you are interested to understand more where we stand in comparison with this process, as I said in the thematic presentation. What we do next, when we recover the silicon, then we transform the silicon in different type of materials. We can transform them in some reclaimed silicon wafers, but we also transform them in silicon powders. And here is a question for you. So you have here 2 images. One is silicon recycled by one of the biggest players in the world, is Recitec from Norway, and the other is the silicon recycled by this project. So it's the same scale, now same tool, taking the image. So it's your guess to say what is coming from Norway and what is coming from SIREVIVAL project. Next slide, please. So Yeah, I can take a question. If you don't guess, I can respond, after the presentation, which is which. So here it's a bit more chemistry. It's from molecular chemistry. I'll not insist. But basically, the ionogels are built with some polymers based on polyethylene glycol. We basically create these subunits, and then we use some specific chemistry. We add the ionic liquid, and we create this ionogel, which is matching very well silicon materials for all, let's say, solid, super solid state capacitors, okay? So again, I'll not enter into details, but I can give you some highlight on this process. So can you put the next slide, please? So basically, when you do this complex precision chemistry and you start with raw materials, and of course you use certain type of energy, electrical energy, you can wonder why you have to choose one ionic liquid or another. So especially if you are in the case we are, meaning that when we change different ionic liquids, we obtain very close mechanical, rheological, thermal properties for the product. And then, let's say, one possibility to say why we choose some chemistry and why not another one is to say that one is less harmful for the environment, okay? And then if you want to have some number behind this decision you are taking, you can do this life cycle analysis, and we do for every product we are building in this process, this life cycle analysis, so we know exactly what is the impact into the environment of every step we are doing, from recycling to building new materials, creating new devices. So we have the full assessment of what we'll have like an end product, okay? So what are the possible evolutions of the objectives in progress of the project? We have some problems indeed with the qualified personnel available in participating teams. I think every agency is reporting these problems quite carefully. So it's hard to find motivated people to work in this field. It's valid in France, it's valid in Tunisia. They actually cannot find these people to be hired yet, both these countries. So then probably we have maybe to focus more on learning more about this recycling of PV panels, because we have this type of end-of-life PV panels not only available in Algeria, but we have them available in Belgium. We have them even available in Tunisia. It was not exactly part of the project, so this to be done in every, I would say, facility. But I think this could be very interesting because we are very efficient. We have a methodology, and then you can compare very carefully what could be done in different locations, and then probably we'll have some aggregated data sets which will tell us more than what we've learned till now, okay? So, yes, so basically I already told you that we are more at the level of assessing this micro supercapacitor, which are built with recycled silicon materials. We are happy that indeed we initiated new collaborations thanks to the results and the work we had till now in the project. And of course, we are trying now to gather as much as possible data to have this life cycle analysis, comparative methodology to be disseminated properly. And yes, we can go further with this type of collaborations, especially if we integrate people from the ICT sector. We can think at more transparency on this, recycling process. We can bring traceability of these recycled materials through digital technologies, and we are working on that even though it was not part of the initial project. I think now we have a lot of data, so this database we have become interesting for people from doing digital technologies. So yes, if we are going on this path, we'll probably be able to have this traceability by blockchain technology at every step, beyond life cycle assessment, as I mentioned to you. Then we can, think on how to collect this panel. What is the right moment to get this panel and put them in this circular economy loop? And of course, we'll definitively need then to be efficient, to scale up, and then we need some automated ultra-fast processes of recycling and avoid more, this manual work and go to more, automatic and sequential work. So basically, this is the last slide. I think we are on a good track with the reinforcement of scientific and innovation cooperation in this sector between both continents. We had several scientific visits in both continents, workshop. I think, yes, we are contributing to help all the partners to have this capacity building in this area of circular economy. And as I said, basically we are interested in getting as good as possible aggregated data sets about recycling and upcycling technologies. And we are interested in building this life cycle analysis together with digital technology. Thank you for your attention. I think was the last slide, right? If I remember correctly, yeah. Yeah.
Okay. Thank you, Sorin, for this presentation. We know that you are expected in another session for a panel, but we will have time, I think, yes, for a few questions. So the floor is yours. Yes, Bernardo. And after Ben Youssef.
Okay, just very quickly, we recently had at least a call in 2022 on recycling of PV, you may be aware of, and we have just signed, and grant agreements have started for the 2 projects that are starting with that. They just started now, September 2023. The projects are called Ever PV and Retrieve, so look them up, okay? Yeah. And if you need contacting them or whatever, just drop me an email and I'll make sure they listen to you.
Yeah, thank you very much. Yeah, thank you for this. Yeah.
Thank you for the presentation. In one of your slides, there is waste of toluene.
Yes.
And considerable quantity.
Yes.
Toluene is...
The functional unit, if you notice, was 1 ton. Yeah.
Yes, so. But toluene is not used actually, because toluene is very toxic solvent.
It is. You can replace it by thermal technologies. We have processes also with thermal technology.
In all chemical processes, toluene is replaced by all BTX, benzene, toluene, xylene.
Well, we still use it.
Cancer cause it.
Yes, the toluene is well known that it's actually very efficient in that peculiar step of removing, from the sandwich some polymers. That can be done completely dry, as I said, by thermal. We have advantages. But then you shift the load from the toluene, or whatever, you see there are huge quantities also of ammonium hydroxide and things like this, to energy, and then you run into another problem. So, yes, this is why I told you that I just discussed, I show you one simple boundary. It is what they did in Algeria. This is why I told you that we have possibilities now maybe to use different type of technology. They also did it also fully with thermal treatment. But as I told you, it's very important to understand if you remove that toluene, what you'll shift. Don't forget that you can recover all the toluene, and that toluene can be purified up to 99%. So it depends exactly what is the chemistry you have behind, and it is the industry which you have behind, because it's a chemical, and once it's produced using a process, and then if you can purify it like people do more than 99%, well, I mean, you have to put down the numbers. I'm not sure, I'm not defending my project, I don't defend my colleagues. I'm just telling you that but people have wrong ideas about what we are doing in silicon technology, about, sulfuric acid, this type of aggressive, solvents and so on. I think you can really easily be misled by what chemistry can do and can use. With the precision chemistry, I am not so sure that toluene, it's a wrong thing.
But it's not a safety solvent. There is orientation.
You just take the safety precautions. You don't have to boil it, on your cooking table.
There is a new orientation of health organization which forbidden use of toluene.
Yes, but I think here it's a very good question. We can run in many, questions about regulations.
And this aspect will affect the scale up and the...
Yes, but many of this regulation, I hope that, yes, I have to be careful what I'll be saying. So these regulations are not necessarily constructive to reduce the climate impact, are not necessarily useful to develop new technologies, are not necessarily useful to support citizens and economies, I can give you examples of other chemicals which maybe don't have to be so regulated because they disrupt, a lot of type of, I would say macro scale phenomenon like creation of aerosol in nature and things like this. And then maybe we'll run soon into a problem because people just see only one side of the problem and they don't see the biggest problem. Again, in this peculiar photovoltaic recycling, I had the same question. I was surprised about the numbers. But then when I read the literature, the efficiency of this process and the numbers, I am not so surprised. And it can be done differently, but I'm not sure it will be more efficient and more useful for the industry. But yeah, we can discuss this. I'll learn from the new projects,
Can I just ask a question about your consortium? Because it seems that everybody has a valid role, and are there any plans for future? So probably I didn't got it within your presentation, but what are you going to do with the project results? With the project outcomes, with the results in the consortium? Did you?
What we'll do, we'll just have a lot of databases with the real numbers done by professional, and then we'll sell them for people which really understands and wants to know what is the value of recycling, for instance. Yeah.
No, I mean probably
yeah.
I was
it's
asking probably if you want to make a startup, for example, or whatever. Yeah.
Startup. It's a lot of work for people from academia.
Yeah, I know.
Yeah. So maybe we can. We are here to help people in African countries to do this. I think in Belgium it's a bit, late to do this type of, business. We can do some other type of businesses related to that, especially if we talk about digital technologies. But yes, I think this, the picture you have seen there are some of the first batches of solar panels which are recycled, at least in this northern part of, Africa. And yes, they can be, They can be aggressive, that they can be, mature, and they can be competitive. But yes, it's very hard for me to tell what they'll do. In Belgium, this business will focus on the digital aspects of the technology, as I said, the numbers, the knowledge, the data sets, what's behind.
So thank you for your presentation. I have one question about one slide. I don't know that represent the energy consumed. I don't know if it is theoretical data or experimental data.
Yes,
about the energy consumed.
Most of the steps are correct. So I wanted to put all the sum to be 100 kilowatt hour, okay? The numbers are pretty much correct because you understood the functional unit is 1 ton, but they are not running the process on a pilot which runs 1 ton, So you have to make some assumption of how you scale these numbers. But if you are used to this technology, what you see there, 100 kilowatt hour for the full system boundary is nothing compared to the moment when you'll start recycling that material. Because if you go to recycle just the 100 kilos of silicon, meaning to make wafers and powders, that number will increase orders of magnitude and you are in the 100 megajoules.
And how you can defend.
I understand your question,
yeah.
but the shift of energy, the energy is not there depending on what to do. On the recovery process, yes, but these are insignificant numbers. These numbers do not count.
And the process, the process by doing the recycling process, it is the doing by electrical energy.
Of course, yes. You have to grind, and you have to grind many hours.
Okay.
Yeah, I cannot give this you. It's quite confidential, but yes, yeah. You can ask Recitec,
Okay.
if
just
they use less power than us.
To add. You said that there is we cannot make business in recycling.
In Belgium, I mean, in Belgium is done. I think it's very hard.
I'm not agree because this is a good opportunity to make a business and to recycle all the PV panels, all the batteries, and this is why we are here to catalyze innovation and to catalyze green technology. To move from the lab, from the lab to the fab.
You need
I'm
tools.
not agree that is not.
You believe me, you need tools, and even from Belgium to do these tools properly is tough. If you do thermal treatment, you basically need to have a full spectrum gas analyzer to see exactly what you put in the nature when you do that treatment. Just a small analysis of this, it's thousands and thousands of euros. The infrastructure is massive. It's not an easy game. So, but if you want to do this business, I'll teach you how to do it, but be sure you have money in the pocket.
This is the role of R&D, to show, to give this data and to show...
yeah, we'll not give it for free.
What is relevant in the recycling or these materials or not. This is the role of R&D, to communicate about this.
Yes, of course, we'll have to do our duties about dissemination. Francois is looking at me with a, with a good eye. So, but yes, it's.
Okay, thank you.
Show how your
yes,
project
yes.
will increase the efficiency and reduce the cost of the recycling.
Yes, I think we are on a very good track to do that. But again, it's more complicated than what you see on the slides or we can discuss today.
Okay,
thank you.
Thank you.
Thank you all.
Very much. So, I propose, thank you. We have still 3 projects. Finally, NANOSOLARCELL is online, but I propose you to have the coffee break right now. We resume in about 20 minutes from now. So it's 4:20, and we will have a project OASES first, and then restart projects and NANOSOLARCELL projects presented. And so we'll have the whole 13 projects presented. So please, in 20 minutes from now, here.
Ginger give me kokoro. Mato de bijo. Tetema. 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 Tetema.
Okay. Hi, everyone. Before we get started, because I'm not going to introduce OASES, otherwise it would be a mess. My name is Karine. I'm in charge of the communication of LIPRI. I think some of you know me from receiving emails from me and prompt to send your information from your different projects so that they can be communicated. So first of all, a kind reminder to send updates whenever you have some to the communication so that we can relay all the good work that you are doing. And second, a practical information for all of you. Tonight the dinner is at Atelier du Vin. We will be departing by bus from this hotel here at the 4 Points Sheraton at 7 p.m. Voilà. So just keep that in mind, don't be late, and enjoy the next session and the OASES presentation.
Whoa, mama tetema. Whoa, mama tetema. Whoa, mama tetema. Whoa, mama.
Maite Lindermeyer, sorry, I have the sound now. So after OASES, we will have another project dealing with recycling, restart projects, and then NANOSOLARCELL projects on new efficient solar cells to complete our review of the 13 projects. So right now, Maite, you have the floor for presenting the OASES project. Thank you. You have 20 minutes.
All right. Thank you very much. While we are waiting, I can already explain you the acronym of OASES, which stands for the Development and Demonstration of a Sustainable Open Access AU-EU Ecosystem for Energy System Modeling. Okay, this is not the first slide. And I'm not sure it's my presentation. Okay. All right, okay. So here you see the first slide of the OASES project, and as you can see, I gave you small hints. There is a starting date which differs slightly maybe from your starting dates, because we agreed on the official starting date of the 1st of July 2023, and this is because it took us some time actually to get the consortium contract finished. However, that was reported, just letting you know, and I will emphasize on this later one more time. So the OASES consortium consists of 7 institutions from 5 different countries. The first one is the Fraunhofer Institute for Energy Economics and Energy System Analysis. That's where I come from. It's located in Germany. The second one is the also German University of Kassel. The third one is the VTT Technical Research Center, which is located in Finland. The fourth one is the Council for Scientific and Industrial Research, the CSIR in South Africa. Just a short side note, they were just hosting us 2 weeks ago for the big consortium meeting, and it was a lovely place, and we had a really efficient consortium meeting, and that's why you get the most recent updates with this presentation right now. The fifth one is the University of Venda, which is also located in South Africa. The sixth one is the Helwan University in Egypt. And the seventh one is, and excuse my French, that's the Centre de Développement des Énergies Renouvelables, or CDIR, which is located in Algeria. So the aim of the project, and I will stick close to the slide at this point, is the development and demonstration of a sustainable AU-EU energy system modeling ecosystem based on open software and open data. The workflows will be demonstrated in energy case studies of varying scales that can be replicated by local actors using the project's code, data, tutorials, and documentation. And in terms of the multi-annual roadmaps, there is relevance for 2 of them. or maybe it's even 3 I see right now. So the first one is this multi-annual roadmap 1, the mapping of the joint research and innovation actions for next step development of renewable energy sources and integration in a sustainable scenario. And the other ones affected are 3 and 4, which are smart standalone systems as well as smart grids at different scales for off-grid applications. Next slide, please. Okay, as you can see, the overall goal of the OASES project is the development and demonstration of a sustainable AU-EU ecosystem, including a well-proven energy system modeling chain. This overall goal consists of 4 sub-goals, which I will now introduce to you. The first one is the provision of data concerning already installed renewable energy systems via satellite detection. And we were doing the satellite detection for wind and PV plants. And in order to achieve it, we used methods with machine learning. The second sub-goal is the generation of open time series data. Obviously, it's needed for wind energy and solar energy. And in order to fulfill this task, we have to develop a tool chain which will allow us to integrate this time series data into the actual modeling workflow, which is basically the energy system modeling tool, IRENA Flex tool, which we use. This is also the third task. What we have to do, we have to develop an easy-to-use energy scenario modeling workflow, which is capable of modeling on local, national, regional, and continental scales. It should be easy to use. All partners should also be able to do so. We want to introduce to you 6 concrete case studies. I will tell you more about them later. And we want to keep developing this IRENA Flex tool. It exists already, but we were adding some new features recently, which makes it even more useful. Last but not least, actually it's a really important part of the project. The foundation for a long-term mission is supposed to be laid with OASES. I think all of you know this with your projects. So we also need an open source and open data strategy. We want to develop a WebGIS application for further dissemination. The example case studies I mentioned before, we want to disseminate not only among the team, but also among local actors, so they can use it as a template and conduct their own case studies with ease. And the last point for the dissemination task is that we link concrete stakeholders to the OASES project. And to measure this, we want to do at least 6 concrete capacity building actions. Next slide, please. So now I want to show you what we achieved by now in the different work packages. I will skip work package 1, since the work package 1 is the coordination work package. So the work package 2 is called Earth observation-based renewable energy source detections. That's where we use this machine learning and satellite imagery I mentioned earlier. So what we did so far is we developed a renewable energy source detection model, which is capable of detecting wind power plants as well as solar power plants based on satellite data. And we trained this model, which requires a lot of processing power, by the way, and we were testing the results. Just as a side note, we also submitted a peer-reviewed publication for this PV segmentation, which is one of the 2 tasks of the work package 2. However, the status is not clear by now, but sooner or later you can access this, most likely. In the third work package, which is called Renewable Energy Source Potential Analysis, right now we completed the methodology for it. So we can do climate downscaling as well as time series generation. And also the CSIR drafted a report, which is circulating among the team right now, with a detailed description of how this tool chain is working. And also part of this tool chain, what we achieved recently is the initiative for renewable energy source potential analysis with scenario-based extension modeling, so that we can identify the most suitable places for renewable energy source extensions in the future. The next work package is the work package 4. This is the energy system modeling tool, which can be used on different spatial scales. So what we achieved by now is that we implemented all the features we want to be implemented in the Arena Flex tool, which one of you may have heard of. Also, we improved the documentation, and there's a bunch of really nice and easy to use tutorials right now, which you can already access by now if you're interested in this tool. We conducted 2 case studies on local scale. They are not publicly available right now, but they will be soon. And also we drafted a concept for 2 national case studies already, but they are obviously more complicated to calculate than the local ones. And at the end of this work package, or most recently, we also have concepted and implemented a modeling workshop. It was part of our consortium meeting in South Africa, and I think like at least 20 participants took part in it, and I would say it was a full success, because at the end it was about 2 days. We learned a lot about how these workshops should be built up, and also we were really enabled to teach the actors on how to use it, which is good, because it means it's actually really easy to use. The last work package is a dissemination, demonstration, and capacity building. And we have a detailed dissemination and communication plan in this work package. And also we have a stakeholder list and concrete plans for their involvement. However, work package 5 was not so important in our process or schedule right now. Obviously, it is first interesting when you have first interim results or final results to share. All right, next slide, please. I want to show you some pictures of what we did by now. Okay. I hope it's big enough for you to see. So on the first picture, all on the left, you can see the wind power plant detection by our satellite image tool in a high resolution aerial image. So you can see all this yellow and red dots on the map. And this means that the machine learning code found a power plant at this point. The second figure is a preliminary result of a PV potential analysis, which we conducted in South Africa. And it's superpositioned exclusion criteria. And you can see the suitable areas for PV power plants in South Africa. If you see anything in this graphics right now which does not appear logical for you, it's possible because it's preliminary, but this is how it will look like at the end. And the third figure, it shows an entity graph of our energy system modeling tool, Arena Flex tool. And as you can realize, it's a really nice and user-friendly tool because it contains a graphical user interface. So that's actually the really nice part of it. It is maybe not as complex as competitors as pipes are, but it's still really useful in order to make investment choices or to model flexibility options in the energy system. And it is really easy to learn. Within 2 days, one can model his grid without any big problems. Next slide, please. So here, it's not a Gantt chart, but I wanted to give you an impression on how far we went with the OASES project right now. What you see in green is what we achieved. So the first task I mentioned is more or less done. And the only thing which needs to be explained here is that the data that we gather with the satellite detection of the PV and wind plants, we cannot use it for the actual modeling workflow. Especially it's complicated for the wind power plants because it's not only the detection and the location of the wind power plant needed, you also need further parameters like the hoop height and the power generation and so on in order to use it for modeling purpose. For the PV plants, it works quite well. However, we decided to use it for validation and not as a basis for our analysis. The second I shortly want to add that the workflow is established when it comes to the generation of time series, but there is still some work which needs to be done. Regarding the third point, I want to highlight, we promised you 6 case studies, and I want to mention, yeah, we will deliver 6 case studies, but we have to be realistic with our resources, and that's why we will especially focus on 3. So the 6 case studies were a local Egyptian one, a local Algerian one, a South African national one, an Egyptian national one, a North African regional one, and a continental one. And we will particularly focus on the Algerian local one, the South Africa national one, and the North Africa regional one, because this is so much work already that we cannot provide perfect continental one. Next slide, please. Okay, I want to speak about the increase in technology readiness level and new developments, which we did in the OASES project. So first of all, we have pretty useful results when it comes to PV segmentation. And the user-friendly code for this software will be available after the publication of the peer-reviewed paper to the public already really soon. Then we increased the tool chains we established at least a tool chain for the conversion of weather data into energy system model data. And for this, we increased the capabilities of AdLight, which one of you may know. And the most significant change in in new developments is the Arena Flex tool, because it includes new features now, such as nested solving windows for investments and long-term storage. I want to speak about the possible evolutions of the objectives in the project and problems we encounter. Unfortunately, we had to start the project 5 months later than we were actually planning to, and the reason was that the consortium contract took us much time and the founding was not easy to get right in the beginning. So we are a little bit delayed, but we are getting up with the initial schedule by now, but still want to mention this, we do not have the same start date as one of you may have. And now I come to the only real issue we have, and that's that the Egyptian partner, the Helwan University, they still did not receive the funding from the national agency, which is the ASRT. So I informed the LIPRI Secretariat, as well as the German funding agency, and everyone is trying to help and to support in getting this funding, but we try already for half a year, and so far nothing happened. The good news is that the Helwan University is extremely helpful, and that the professor, who is the coordinator from the Helwan University, he is still working with us. He is supporting us, and he is really nice. He is providing all the data needed. But it's still not the best situation for him right now, because he also needs to finance his team, and this would be maybe something we need to discuss, and hopefully we can find a solution for this, especially considering that the importance of Work Package 5 is crucial, because the dissemination and capacity building is a vital part of the project. Next slide, please. When the project ends, we have some planned follow-up work, and the most significant one is that 6 of 7 parties of the consortium agreed 2 weeks ago on going for a successor of OASES. So we are looking really systematically for new funding opportunities, both in Europe and in African Union, and we have a really strategic approach when it comes to this. Yeah, regarding the become of the consortium set up on the project, I just want to mention that the consortium gets along really well, and this I mean on a professional as well as on a personal level. It's really fruitful work, and it's also fun. We started to exchange in a matter of other projects too, which I think is a little bit what is LIPRI also aiming to establish. And as I mentioned, most of the members, they want to continue working together. When it comes to new collaborations and future planned collaborations, yeah, we publish together already by now. I mentioned this paper before. And there are formal declarations of cooperation between different institutions already by now. So they want to exchange students, they want to exchange stuff. And this is, for me, also really positive development, because it's definitely something long-term and some African Union, European Union connection. Yes, then we are cooperating close together regarding this energy system modeling tool, obviously, and we are planning to have even more further formal declarations. Next slide, please. If the project succeeds, and I think so, even though we are facing these funding issues, there will be mainly two outcomes if you look at a broad scale. The first one is in terms of technical development. So what we are doing, this resource assessment, is still crucial for some sources, because when one wants to deal with the integration of renewable energies in different grids, this person still needs need to make a lot of assumptions and needs to gather a lot of data. And we make process in this resource assessment. For example, this recognition of the power plants is really helpful in countries where you cannot really find data regarding the installed capacity. It's one step, but this technological developments will definitely be a positive outcome of the project. And obviously this data is needed for the energy system modeling, which is crucial for the integration of renewable energy sources. The second point is that we bring renewed attention to energy scenarios and policy. And this is really important to understand the context in which technologies and energy solutions will be developed. We want to help to minimize unforeseeable consequences. One may use our tool in order to plan their capacity building, or not their extension actions, and we can support them with this. And also, there is a clear need to support further research as well as capacity building on energy scenario analysis. So we bring a new modeling approach, and we highlight that there are those modeling approaches, and we provide tools that support policy and decision makers to build a long-term plan for their country or even at regional or continental level. Next slide, please. So when you look at OASES and you ask yourself about the contribution of the project to the African Union, European Union Research and Development Partnership, there is already, thanks to the project, existing, but there will also be upcoming collaborations between both continents. In the context of the project. We have, as I mentioned before, the clear intention for new intercontinental projects, and I'm quite sure that they will appear sooner or later, as soon as there is a possibility for founding. Our capacity building actions enable African partners to use the technology developed, and they can, at least in some country, really make use of it. The Arena Flex tool is really easy to use, and it addresses the challenges on the African continent quite well. And we have a regular as well as benevolent exchange between the actors from the two continents in the context of OASES, but also of other projects. So do we want to participate in other LIBRI clustering activities? The answer is yes, there is a general interest. We will also share our results both in terms of RES detection as well as Arena Flex tool. And also we will host more Arena Flex tool workshops, so other LIBRI members, they are invited to join them. And if there should be other clustering activities and we will be invited, we will definitely also join. So all that's left for me to say now is thank you very much for listening, and I hope you have some questions.
Thank you, Maite, for this presentation. Just before taking question, I will react on the issue of lack of funding so late in the project implementation. In this kind of scheme or co-funding from national agencies and with the support of the EU Commission, it's quite complex since there is several, for one project, you have at least 4 funding agencies, and of course there could be issues regarding the funding agencies that has to contract. There is also sometimes some documents required by funding agencies in order to be able to contract. And in the case you mentioned, we were involved to solve it. For example, we discovered that there is not only the relationship between the funding agencies and the partners in Egypt, since you said that there is also other bodies, administration, who should give authorization to the university to receive the fund from the funding agency in a multilateral context. So it's very difficult to say, okay, the problem is just due to the funding agency, which is not enough speed, but sometimes it's quite very complex, and we try to solve that. And I hope for OASES and another contract, it will be solved soon. Okay, it was just a precision because it needs to be very difficult. Okay, Bernardo, sorry.
Thank you. Too many microphones. No, thank you very much for the presentation. I mean, it sounds extremely familiar. We just held a session on energy systems modeling this morning, just one floor up. I don't know if you were there or not, but definitely, please, please, please talk to them. I mean, everything you have talked to us about today, they have your same common problems. And I mean, just to identify a few, reaching out to authorities is typically complicated. I mean, it's something all the other projects I've mentioned as being an issue and a problem, and something where if you pool together, you will have better access. And the other projects some of them have different geographic coverage areas than you, but they're mostly using the same open source tools than you. So maybe it's worthwhile to understand with them how you can share data, because you will probably or maybe have some common areas where you have to source the data and they have that data available. And yeah, please, please, please. I mean, this evening you've got a nice evening lunch to look forward to. I'll try to give you the names of these people and I'll make them aware that you're there and talk to them. Because yes, I mean, especially for modeling the difficulties in the area, be caricaturizing, you're basically building SimCity for policymakers, okay? So, I mean, it's a broad caricature, but your target group is the same. And you will be facing probably the same type of issues when addressing them. There are also common areas of cooperation which I think are no-brainers, which is interoperability. I mean, the tools that you're developing, since they're open source and they're addressing more or less the same type of issues, it makes sense that at least you can benefit from each other's developments. It's another no-brainer. And yeah, data exchange protocols, I mean, everything they can think of in software development. So also validation. I mean, you can use each other's tools to validate each other. I mean, those are things off the top of my head this minute. So yeah, please talk to them. I mean, we've got there are the projects within Libre. And we've got also 4 other projects too that are dealing with water, energy, food nexus. One of them is OpenWatt for Africa, and the other one, I wish I remember the names. Okay, I'll get you the acronyms in any case, and the contact names of the people so that you all get together and decide how you're going to do things together. Because, I mean, it's a non sequitur. Please do things together. Thanks.
Okay. It's rather a recommendation and a question. I don't know if you have some. Okay. Otherwise, if there is a question, could you stand up if there is a question? I don't.
Okay.
Sukaina. Go ahead.
Thank you for your presentation. I have just one question about what you have presented regarding the algorithm that you have developed, because you said that it detects wind plants or PV plants. What is the objective behind, or to detect if there is a PV plant or a wind plant, because I thought that is describe or develop the potential of to develop PV plants or wind plants. And what is the difference between your platform and what is commercially used today, PVCs and others, and other platforms that can develop the potential of PV or wind plants? Thank you.
So I'm not sure whether this microphone is working. Okay. All right. Then regarding your first question, so there is definitely a use of being able to detect this wind and PV power plant. And the reason is that there is not good proven data available in all countries. So in some regions of the world, you will find really nice data sets, which will tell you where are all the wind power plants, what's their hoop height, what's their generation capacities, and others you will find not. Or in South Africa, there's a lot of shadow capacity of PV power plants. So if you can detect them with your satellite detection, it's way better than using publicly available data sets.
But this data can be found in the Ministry of Energy in such country.
Often, yes, but not always. And as I said, for example, in South Africa, there's a lot of shadow capacity which is not registered. The people, they just put PV panels in a huge scale on their rooftops in order to fight the load shedding, but they will never register it.
And it can detect if it is off-grid or on-grid connection?
No, it can just be detected, not more, not less. You cannot make any conclusions regarding the grid connection.
Because we need this kind of data to communicate, for example, for EUA, PVPS, the total capacity installed in on-grid and off-grid. And it is difficult to separate from.
But you can combine our approach with the analysis of the flow in the grid, and then you have a quite clear view on the things already. Just an example on how you can use this data. In general, to answer your other questions shortly, it's also important to have this data for the energy system modeling workflow as well as for the extension, because when you want to model the extension, you need to know where is installed capacity already. And our tool is different than other energy system modeling tools. They all have some similar things, and they differ. And they differ often in the methodology and in the way they optimize the problem. And I think Arena Flex tool is a really handy one, and it is also the big difference to most of the other tools, also commercial ones, is the graphic user interface.
Thank you very much. I have a question about the climate information. Yes, it's about the climate information. So I mean, how to provide the climate time series that you mentioned. So is it done by only one partner, or every case study is the partner concerned by the case study is doing its own climate information? Thank you.
Yes, okay, just short answer. Now we combine the competences of different partners, and mainly it's the CSIR as well as the Fraunhofer IAE, which is basically my institution. And we combine the competence of our in-house tools from Fraunhofer IAE with AddLight, and also we add another features, and then also the local partners for each country, they will double check and validate our data. So there's definitely frequent exchange among the partners.
Thank you. Your computer.
Okay,
yes. Thank you, Maite. So we will go now to the next presentation, which is a restart project on recycling of PV components. Ismail Sadoun is online, I think, so I will give him the floor for 20 minutes sharp, please, because we are running out of time. Thank you. Is your microphone open, Ismail?
One is open.
Okay, go ahead.
Okay, could you please go to the first slide? This is the second one. Okay, So thank you, Mr. Chairman. I'm so sorry. My voice is not 100% okay because I'm sick, but I will do my best to present our project. That is the progress of a project that is on behalf of my partner from the consortium, formed by five institutions. If you can go to the second slide, please. So the consortium was selected to get the full chain to tackle this issue of battery component recycling and use the recycled metals for fresh batteries to prove the concept. So the consortium is composed from Qadi University, funded by the Ministry of Higher Education, Moroccan one. We have Egyptian King Salman International University. I will be back to this point later, but you mentioned this issue with also the previous project. We have Aalto University from Finland, Cerej from France, and also UM6P and the Green Energy Park that was funded by Irizen. I think Sukaina is there. Greetings from Morocco, Sukaina. So the aim of the project is to implement a full value chain for recycling end-of-life battery, but also some PVs, and we have somehow the same objective than the SIREVIVAL project, who also is devoted to recycling silicon from end-of-life PV photovoltaic panels. So the specific objective is how to collect, which is a big issue, how to collect end-of-life batteries from the trashes, from used person, how to recycle, which is somehow a technical part of the project, and then we have the soft part of the project, how to implement, and finally the coordination of the members was also one big task for this project. So we will ask to highlight the relevance of this project with the Mars. So I bring there some point. We have the map of end-of-life component value chain, identification of second life component with benefit of African countries, dissemination of acquired knowledge, creation of jobs, because the aim of this project, how to create startup, starting from end-of-life electronics waste, and also the promotion of environmental and ecological sustainability approaches. Next, please. So, next. Yeah, thank you. So before giving the progress of project, I would like to introduce some vulgarization of what we are doing. So all of you are using lithium-ion battery in your smartphone, on your computer. It's composed from two cathode and anode material, which cathode is a material composed from some critical materials, and the anode side is graphite, and in between we have some plastic and so on. And if you see the lithium-ion cost breakdown, we have this cathode material cost represents like 35% of the total cost of the battery, and the anode side is roughly 10% of the cathode. So it's good business to do when recovering this cathode and anode material. Of course, the other component like a copper, like a plastics and so on are very important. Why this project was interesting? Because as you see here at the right side of the slide, there are a huge number of application and production of lithium-ion battery that is expected in 2040 or much more. This means that we will have two big issues. One is the need of raw materials to face this energy transition for mobility or for integration of renewable energy in the electricity sources. And also, you should develop new technologies beyond lithium-ion battery, but this is another topic. The second biggest issue is the environmental issue, because end-of-life battery contains some issue regarding their impact on groundwater quality. So recycling is really the best way to make this a circular economy, and then do not put this end-of-life battery in the waste landfills. So coming back to the cathode material, if you know the topic, In the cathode material, we have a lot of chemistries. We have what we call the NMC chemistry. This means that you have nickel, manganese, and cobalt in the cathode material. In Ca, that means that you have nickel, cobalt, and aluminum, lithium cobalt oxide, or lithium manganese. In the anode side, you have normally graphite, but now people are trying to introduce silicon because silicon introduces high capacity. This means that you will maybe get much more time to recharge your battery in the future, which is a very hot topic for the future generation of lithium-ion batteries. Next slide, please. Yeah. Also, I would like to highlight this. I took European Union as an example. There are a big critical raw material act that was implemented in Europe. And you see here, I represent the lithium, graphite, nickel, manganese, cobalt, and you see that there's high criticality of these metals. And European Union, but also America or China, will depend a lot of import of many critical raw materials that exist in Africa, as you know. So to recycle this battery, there are a lot of process. Yeah, we have some pyrometallurgy process, hydrometallurgy process, biometallurgy process. But the methodology, how to collect, how to develop this process is a little bit complicated. I will give you two examples that we were developed in our consortium. Just to mention also that Europe's target is to rise to 20% for recycled cobalt, 10% for recycled lithium, and 12% for nickel to produce the next generation of EV. And we were witness lately to do many gigafactory coming to Morocco, but also some African or European. And then they will need some recycled cobalt, so recycled nickel to put in their battery if they would like to export to Europe. Next, please. So let me remind the consortium methodology or work chart. So there are a lot of work packages. So there are what I said. The hard work is work package 1, 2, and 3, which are aiming to develop process, to recover, to collect, and then to produce high quality, high purity cobalt, nickel, manganese, and lithium. And then when optimized, then we'll go to the soft part of the project to develop this proof of concept, but also life cycle assessment and technical economical assessment to go further for this business model to implement this startup. So just to give you an idea, this is a picture we're taken from our lab here in Morocco. So we received end-of-life batteries from this partner, which is Imob e-scooter company. And then this discharging, very important to discharge this battery and then to isolate the modules and then dismantling to separate plastic shell, separator and so on. And then we can have access to the anode and the cathode side of the modules. And then we develop chemical process to recover cobalt, graphite, nickel, manganese. And you see here, we put the cost of each component, but are directly extracted from the website of many chemical supplier in Europe, but also in America. So the key challenge is to collect, disassemble, and characterization of this end-of-life lithium battery to technical development and scale up. This is very important because now we are developing process, but the next step will be how to scale up this process. And then demonstration, because what we do is when recovering this metal, we build new cathode material and we build new fresh battery, and we see if we succeeded to have a high performance like for metals directly received from the suppliers. So we have to develop the economy business around this and dissemination of cost and of course implementation of startup. And I put here in red this big issue of Egyptian partner. Of course, the eligibility of our project is to have 2 partners from the south and 2 partners from the north, but we have 2 agencies acting in the south, Erizon and the Ministry of Higher Education from Moroccan side. And from the north, we have 3 agencies. We have Ceneres, we have Romanian agency, and we have also Finnish agency. But this point, as you said before, will be fixed soon, inshallah, as we said in Morocco. So the results, I will give you next slide. We will have some publication. I will give just a summary. The progress is are successful except the work package related to the Egyptian partner. But what we do, the work package that initially was given to this Egyptian partner was now recovered by the Moroccan. We are doing the same activity that normally was affected to this partner, to our partner. The TRL, we are in TRL 3, I guess, and the objectives are partially achieved. The activity initially active to Egyptian that, as I said before, is redistributed among the other partners. Now we are in this process development, which is very important for the project. Next, please. So we have a lot of production of participation to conference or so on, but I select two papers that were recently published in 2023. The first one is under the collaboration between QDSOC, UM6, PGUP, and SIREVIVAL from France. So we put a PhD student that was the scholarship was granted by GUP and SIREVIVAL, what we call the thèse en co-tutelle, who supervised the PhD. So what we do, we select the less complicated chemistry, containing only cobalt as cathode material. So the flow sheet is like this. We discharge the battery. We separate manually the anode and separator, and then we have this hydrometallurgy process that we recover aluminium by adding NaOH, and then we have this leaching process using some some strong acid to recover cobalt and so on. And the last cobalt was used to produce lithium cobalt oxide and tested in the battery. The more detailed methodology, result, and so they are inside this paper with the impact factor not so far from 9. The second process, please go to the next slide. The second process, as we call molten salt. This one was also done by the second PhD student, who is funded by Horizon during the project. And then here we propose this molten salt. So the first steps are similar because we should have discharged correctly the batteries and then recover aluminium. And after that, we put this what we call molten salt. Molten salt are a salt that melt at very low temperature, so we can reduce the cost and then recover all the metals. And after that, we recover this hydroxide of nickel, manganese, and cobalt that we use to produce a new cathode material. Of course, lithium source is also recovered from the process. So we are doing some assessment to recover everything we use and everything are present in the battery. And the leaching efficiency is reached almost 95%, 94% for lithium, manganese, nickel, cobalt, which means that we succeeded to extract the maximum of the metals are present in the lithium-ion batteries. Next, please. So the end of project is 2025. We are in midterm. So the planned follow-up is to scaling up of the most efficient process. We are now in this process of to select the right process and to select the right condition, because there are a lot of parameters that impact the process, like temperature, time, the nature of the leaching process, and so on. We are doing technical economic assessment with the help of the Romanian partner, which is very expert on that domain, and also this life cycle assessment, which is really important if we like to implement something, a startup. And this part is ensured by the Finnish partner. So the become of concern is the creation of the startup and submission of proposal, of course, supervision. New collaboration, of course, we have two big collaboration. We were approached by this UNESCO chair on e-waste recycling from Polytech Montreal to join the consortium. We planned to meet 15 or 20 days ago, but unfortunately with the earthquake in Marrakesh, we postponed our meeting to November. And we have this CESA project, which is a sister project of LEAP Air, where we have to develop three demonstrators. One is rural, one is electromobility. And for those two demonstrators, we will use batteries. And of course, we were trying also to implement this demonstrator of recycling batteries. So when within CESA project, if we validate the three demonstrator, rural, urban, and recycling, we will replicate in many countries in Africa, namely in South Africa and Kenya and Ghana. New collaboration, until now, no, but just 1 second, please, before. Yes, we were also involved in this new project we called AirClip, which just funded, we just started. Next, please. So the expected outcomes is the characterization, separation of metal product is already done, development of efficient metal extraction process done, development of lithium battery, a new battery done, but this part now in red or in orange are in progress. And we hope that in the near future, we can start by doing this activity. But our partner in Europe already start to implement, to simulate all these things. For instance, all people now are looking for battery with less cobalt, but now nickel will remain a big issue. Not thanks following the crisis between Ukraine and Russia, and they are producing nickel. And now the direction of battery producer is how to reduce nickel, but it's like a game. We will not understand, we will not predict what will go in the future. Of course, the job creation through this startup, which is a big progress, that could progress to the small or medium enterprise. So I think it's the last one. Yeah, thank you for your attention. And if you have any question, of course, you are welcome. Thank you.
Thank you, Ismail. Thank you very much for this presentation of Restart project. I will not come back on the issue of the situation of two Egyptian partners funding. So I will take the question from the floor here in Kigali first. None? Okay, maybe people began to be tired, so. Sukaina, no, you don't raise your hand. Okay, Bernardo.
I mean, I make the same comment I made for the previous project on PV recycling, is that we do have two projects that have just started that deal with PV recycling, of course, at a different scale, but in Europe. I'll make sure to give them your contact so that you can talk to them. I mean, they just started, so probably they haven't gone very far. If I remember correctly, the acronyms are, I knew them a few minutes ago, EverPV and Retrieve. Okay.
Yeah.
So these are dealing with PV recycling more specifically, but we do have in our portfolio of projects a very broad range of batteries project that do have as main focus recycling, and I would encourage you to look at the BAT4EU partnership strategic research agenda that has just been published. There you will have any manner of ideas of what to do further.
Yeah, I am, as I said, I am partner of AirClip partner project.
Great.
Okay, thank you. Just before going to the next project, I will say again that we are discussing with ASRT, which is doing its best in order for the university in Egypt to get the authorization to have a contract with ASRT. So you saw it's complicated, but ASRT is doing its best in order to solve this problem. And I hope it will be solved soon.
Thank you. We hope so.
Thank you. Yes, Sukaina, you have a question?
Okay, just about the reaction of the other projects which are in the recycling also. When the question was to create startup, and so I don't know if Mr. Sadoun can give us a quick business model of the future startup, that the key activity of the startup is recuperation of all the batteries and the recycling materials of batteries. So I don't know if it can be possible at this stage for Mr. Sadoun to give us a quick business model. Thank you.
Okay, thank you, Sukaina. You are following my project in the Moroccan side.
Yeah.
So, yeah, we are, as I said before, we are just finishing the hard part, which is technical part from the project. And to go further for the business model, we need to implement this life cycle assessment and technical economic assessment, which will start soon. So I can't answer directly to your question now, but maybe the next month we will have some clearer idea for this business model, of course.
Okay. Thank you. Thank you very much, Ismail. So we will go to the last project to be presented today, which is the project NANOSOLARCELL. Conchiania, she's online, will present the project. Sorry, since it was first scheduled at the beginning of the afternoon, but you were not online, so we had to postpone it. So you have the floor, Conchi, for 20 minutes, and after we'll have 10 minutes question.
Okay, yes, thank you very much. Can you hear me? Yes?
Sorry?
Yes, good. Yeah, I can see my presentation. So thank you very much, and I apologize for the inconvenience in the connections before. But it's at least it's a good news that I can present the outcome of our project NANOSOLARCELL today. In this first slide, I have we were asked to introduce the dates of the project, the starting and the ending. So as you can see, I am. Let me just show. I cannot see. Yeah, okay. I thought I could use a pointer, but not. As you can see, the starting date, I am including those of France, who is the coordinator of this, and as ending date, I am considering also the date for France, but also 2026, because as it has been raised by many other colleagues in the projects, we have different periods for the implementation of the project. If we can move to the second slide, please. Yes. In this one, I will introduce first the consortium of this project. The coordinators is CNRS Laboratory SMT, which is located in Orleans in France. It is centered in the Institute of Chemistry of CNRS, one of the largest institutions in France for research. And the project partners come from Algeria, Egypt, Morocco, and Romania. In the case of Algeria, the participation is led by Professor Ayat, which is coming from the Center of Development of Renewable Energies from the Unité de Développement des Équipements Solaires, UDES, which is in Algeria. In the case of Egypt, our colleagues are led by Professor Salak from Mansoura University, belonging to the Faculty of Science. And for Morocco, it's Professor Al-Magousi, who is leading the team at University Kadi Ayat. And finally, our Romanian team, it's Professor Stan, who is leading this team from the Faculty of Chemical Engineering in the George Asaki Technical University of IASI. As I've mentioned before, we have different timings and not only understanding and finishing dates for the projects, but also for the duration of the projects, which Sometimes it varies between 2 and 3 years. We are perhaps very naively optimistic, but we think that we can keep up with the collaboration after the project for those of the partners that will be finishing earlier, so that we can still comply with the goals of the project. Just as an indication, for the coordinator, the end of the project will be April 2025. For the partners in Algeria, it will be 24, the end of 24. For the colleagues in Egypt, they have started in mid-2023, so just started, where the rest of us had one year. And so they will finish by mid-2026. And in Morocco, they will finish in August 2025. And for the Romanian partners, they will finish in December 2023. Although, as I said before, we also have some other collaborations, particularly as the coordinator. So we are pretty confident that we can keep the collaboration and the goals. So concerning the project, NANOSOLARCELL is about the integration of photonic conversion layers based on quantum dot nanostructures that I will explain a little bit before, for improving the conversion efficiency of different photovoltaic solar cells. So as you can see in the section of the M of the project, so we want to use the so-called down conversion layers, which are based on nanomaterials which are photoemissive, and in a complementary way, as I will introduce later, on compared to the materials that are already the main constituents of the photovoltaic cells. And with these down conversion photonic layers, we are going to increase the conversion efficiency of the overall device, because we will exploit a fraction of the light which is not currently exploited by the existing devices. And even if the conversion efficiency increase is expected to be between 2 and 3%, we do believe this is pretty important in order to improve the amount of light that can be harvested in the photovoltaic cells. So another important goal of the project is that we will develop the materials in these photonic layers, and we will test them in devices at large dimensions in order to evaluate the performance not only at the control irradiation conditions that we can have in indoor in the lab, but also outdoor illumination, and where we can test the durability of the materials in outside and in aggressive environmental conditions in African countries. And in this case, we will profit from the facilities that our colleagues in Algeria have for the construction of these small prototypes, and to check the lifetime and the efficiency and the real conditions of the materials which we will prepare. Regarding the relevance of the multi-annual roadmap of this project, of this call, NANOSOLARCELL had focused on topic 1, which was based on, well, you can see it in here, in mapping joint research based on renewable energy resources and sustainable energy scenarios. I think we can also select or think that our topic is relevant to topic number 3, which is smart standalone systems, because we aim to improve a technology which is already on the market by doing a slight modification, as I will address in a few minutes. So this can have a real impact, because it's a technology that can be modified and improved, and in the short time of the project, we don't need to go to develop from scratch, from the TRL levels very low to very high. So, however, there is a main challenge on this approach, which is to once we have the right conversion layers, as we do, to integrate them in these existing devices, and for that we have to adapt the properties of the materials to the different configurations of the photovoltaic devices, not only considering silicon-based, but also some other types of solar cells, such as organics or dye-sensitized solar cells. And to try to test them all in these outdoor conditions in realistic UV irradiation in the presence of aggressive environments such as atmospheric pollutants, rain, dust, and so forth. Can we move to the next slide, please? Yes, these are on the left-hand side of the screen. You can see which are the main scientific and technical objectives, with some of the details, keeping in mind this development or the improvement of the conversion efficiency of solar cells by the using of photonic layers. So if we look at the specific objectives, we need to design the photonic layers, which are based on down conversion system and based on photoemissive materials. One important thing that I did not mention before is that we are going to use materials which are extremely low cost. These are based on carbon, on quantum dots. I'm sure that after hearing the news on the chemistry Nobel Prize of this year, you're all aware of what is a quantum dot. In our case, we focus on the utilization of a specific quantum dots, which are made on based on carbon, which is one of the sketches that I've introduced in the right side of the slide. The importance of these carbon quantum dots is that we can get them from renewable resources that can be locally available in mostly all the countries. So just as an example, we can get them from biomass, from the processing of biomass. And this is extremely important because the manufacturing and the fabrication method, it's based on non-very energy demanding processes. And therefore, they can be implemented anywhere in the world. The second objective is, of course, to establish which are the best operative conditions for these different down conversion layers, depending also on the commercial solar cells that we have, to be sure that we have a low cost on these, that we don't have to do any extra functionalization or any further modifications that will increase the energy demand and therefore the cost of the photonic layers. And the main one, which will be developed in the final months of the project, which is exploring which are any agent or deactivation mechanisms that we may get by incorporating these photonic layers. And as mentioned before, the durability of the devices in these aggressive environmental conditions in outdoor experiment. So, but just for those who are not familiar with this down conversion process, I will address it briefly so that we can better understand which is the approach that we target in NANOSOLARCELL. As you can see in the upper graph in here, this is a representation of the spectral irradiance depending on the wavelength, which is an example, for instance, for the silicon-based solar cells. You can see in green, which is the fraction of light, which is effectively used nowadays for this kind of devices. The situation does not really change that much for other types of solar cells. And as you can see in red and blue and purple, there is a quite a large amount of energy. You can have here an estimation in watts per square meter of the spectral irradiance, which is not used coming from the solar light, which is not used by the commercial solar cells. So by incorporating these photonic conversion layers, in the case of down conversion, what we are going to do is to profit from this fraction of light in the UV, the purple and the blue areas in here, that currently they are not only not used in the solar cells, but also they are detrimental for the functioning of the solar cells, because they are usually very aggressive and they can damage. They damage, in fact, the performance of the solar cells, reducing the durability of them. So if we are able to transform this amount of energy, which is wasted nowadays, into other energy of lower, in other photons of lower energy, then that we can re-inject in the system, we will be increasing the overall conversion of the solar cell. This is what we do with the so-called spectral converters. And in our case, we focus on the downshifter or down converters, which basically consist in absorbing these high energy photons that we have in the UV that are harmful for the cells, and then we transform them in a lower energy photon, which can be directly used because they enter in this gray green area of the wavelength, so that we can have either a 1 photon or a 2 photon conversion process. Depending on that, we have different mechanisms, but in any case, what we have is to adapt this absorption and emission of the solar cell that we are targeting. And we plan to do this with this carbon quantum dot. So can I have the next slide, please? Can I have the next? Yes, thank you. So the project is divided in 4 work packages. The first one is the coordination work package, and the work package 2 and 3 are those related with the scientific development of the design of the photoemissive layers, the synthesis of the materials. This is the work package that has started for the past year and in a few months. Work package 3 is the implementation of the conversion layers that we already have prepared into the photovoltaic cells, and then the last one is devoted to communication and communication of the project outcome and networking with other projects. So regarding work package 2, this is where we have started in the past months. There's mainly 2 partners, CNRS and IASI, who are working on this synthesis of the carbon-based photoemissive layers, these carbon quantum dots. I have introduced in here a microscopy, which is where you can see, perhaps, I hope, the dark spots of lower dimensions than 10 nanometers, which are the representation of the evidences of these carbon quantum dots in the microscope. We are using different approaches for the synthesis. One of them is a flash calcination at moderate temperatures. And here we can use either organic reactives, and this is the N-hydroxyphtalimide that we have used as a reference because it's a material that we know it has the correct photoluminescence properties that we need in order to induce this down conversion process. But we also have tried to get them from biomass. This is an example of pine needles that we are using here at CNRS, but in collaboration with the partners from Morocco, we're also using argon waste, which is something which is very abundant in Morocco. So we can also introduce some metals in the synthesis, which are not precious metals. They are abundant metals, so that in order to keep in mind also the sustainability and the low cost of the catalyst. And we are also using another method, which is the electrochemical exfoliation at low voltages of graphite residues. In other case, we can get carbon dots which have different photoluminescence properties. And these photoluminescence properties is important because they must be able to absorb in the UV, which is the part that I have introduced in here in blue. You have the absorption spectrum of those, as an example of the carbon dots that we have prepared in the presence of copper, iron, and cobalt. You can see that we have different peaks because they show different ability to absorb in the far UV or in the near UV. And once they are absorbing in this range, we have to be sure that they have a photoluminescence properties, which is what we see in the second part of the plot down to the right, that you can see that regardless of the light that they have absorbed in the blue region of the plot, we do have the same emission properties. This is interesting because we are precisely looking for materials which can be excited in the UV, as I have indicated in here in this sketch on the upper right side of the slide. And after UV excitation of these carbon dots, we have a blue emission. This blue emission is characteristic of the photons that have a much lower energy and can be injected in the existing commercial solar cells. Then, of course, we have been optimizing the conditions of the synthesis in order to change the temperature and also the reaction time and so forth, and investigating which are the photoluminescence properties of the materials. This has been the core of Work Package 3, of Work Package 2. If we can move to the next slide. Yes, Work Package 3 have started for the rest of the partners from during the summer, from August or September 2023, and it's based on the integration of these materials that we have prepared so far, and now we know they have the correct emission or photoluminescence properties on the different photovoltaic devices. For doing that, we are taking different approaches. The first one is that, as I've mentioned before, we have to adapt the incorporation of these layers to the solar cell devices. In the case, for instance, of silicon-based, we are planning to immobilize the carbon dots in a thin, transparent polymeric layer, as I've introduced here in the objective number 1. And where we can use them to cover the surface of existing devices. I have introduced here some examples of the polymeric thin layers that we have prepared so far. These are the very recent results of our partner from Romania, where you can see these transparent hexagonal polymers, which have, in the absence and the presence of the carbon dots, and you can observe that they do have this still keep the photoluminescence properties, which is an important property once we want to introduce them on top of the solar cells. We have also the same effect when we do this for other carbon dots, which are emitting in the red or in the green. So where we are right now is that we need to keep optimizing the layers in terms of transparency and in terms of thickness, and we are working in collaboration with our partners from Algeria and Morocco to incorporate them to silicon-based solar cells. Another approach is to incorporate these in different organic cells, such as perovskite-based or dye-sensitized solar cells. In this case, the coating, the photonic layer will not be in the external part of the solar cell, but as a part of the electrodes. Here you have a configuration of the perovskite base with the metal contact, the whole transfer layer, electron transfer layer, and the active layer. The idea is to verify where this photonic layer can be more active or more beneficial to improve the performance of the solar cell. And this is what we are starting to do. This is one of the images of the first semi-cell that we have prepared with perovskites. And here you have some IV curves of the materials that we have, of the cells that we have prepared in the presence of the carbon layers, where we have been playing around with the position of the carbon layer, either in the composition of the active layer, the perovskite base, or with the ATL or the HTL. And as you can see, there is a huge difference in some of the important indicators of these materials, which are the open circuit potential and also the limiting current density.
Conchi, sorry, you have 2 minutes left.
Yes, I'm concluding. Okay. So regarding the expected results, I have included the midterm and those at the end of the project. The midterm results are to be able to demonstrate that we have at least 3% increased efficiency in these solar cells after the incorporation of the photonic layers. Also to start constructing the prototype, and to contribute to train young researchers. And I have introducing here some of the markers that we have gotten so far, which are the co-direction of PhD students between partners, one patent filed on the deposition of the carbon dots on these transparent polymers, and several communications to international conferences. Regarding the expected results at the end of the project in 2025, main two are to achieve at least 10% of increased lifetime, so with the durability of the test, and at least 10% reduced cost on the fabrication of these devices. If we move to the next slide, I think it will be my, this is just a summary of the expected outcome. The next one, which is my last one. It's, I'll leave you here perhaps if you have some questions about the contributions that we think our project NANOSOLARCELL can make to strengthen the cooperation between the European Union and African countries. And also I think it is important, and I did not include it in here, but we are very much interested in having interactions with other projects funded by this call. So far, we have started networking activities with another project from the Marie Curie European funding, so it's not a Libre funding, that was based on international cooperation for the development of perovskite type hybrid tandem solar cells. And we have been exchanging with the different partners in order to detect the common interest from photovoltaics and to see whether we can also introduce our photonic layers in their materials. So I think I ran out of time, but this was my last slide. So thank you very much. I'll get any questions you may have. Thank you.
Thank you very much. Okay, thank you, Conchi. We will have some questions from the room. Maybe. I think everyone is quite tired after a whole day of presentation. Bernardo?
Sorry for playing the bad guy. So late in the day. No. Just two small questions. So you were talking about an increase in lifetime of 10%, right? Increase of lifetime of what? Of the lifetime of the quantum dot layer, of the whole perovskite cell, of what? For me, it wasn't clear. It was so fast that I couldn't follow up.
Yeah, I'm sorry. Yeah, the idea is to get an increase in the lifetime of the whole device. So
the whole device.
Yes, the solar cell. We have to say that one of the main factors for decreasing the performance of the solar cells usually is the large contributions of the UV photons.
Yeah, UV solar degradation. No, that's clear. But the question I have here: are you talking about the whole device, and is it specific to perovskite devices? Is it specific to other devices? And my question is whether the down conversion layer itself does have a lifetime issue. So what's the lifetime, the degradation of that layer itself?
Yes, we have. So in the case of the solar cells, it is more important for the perovskites because, as you know, they are much more unstable than silicon-based, particularly under UV, also under humidity. So the role of the carbon layer is going to be much more important in these. But it's also important for the perovskite. For the silicon-based. So that's concerning the first one. Concerning the stability of the photonic layer itself, since the starting of the project, we have been submitting some of the layers to irradiation. So far, we have continuously 9 months of irradiation with the solar simulator of the best layers that we had. And we still observe the transfer, the photonic transfer, the conversion that we are looking for. And it's well, we have to demonstrate that it's going to improve the efficiency also of the overall cell.
Are you going to do the IEC testing, ISO testing, and so on and so forth? You know, X hours. I can't remember the exact parameters. It's 8,000 hours at 80% humidity and so much degradation. You know what I mean? I understand that for your specific layer, you will not have a standard developed for it, but I guess that if you are going to apply it to other PV technologies, you should at least look at the existing standard and seeing whether how much your layer would contribute to the other cell complying to that, and whether your layer would actually comply with that. Those were the two questions. But I mean, we could get on with this for hours. So that's one, and the improvement of efficiency is 3%. 3% relative, I understand, right?
Yes.
Okay, good.
Yes.
Those were my two questions. Thanks.
Just on the issue, recently I heard in a conference on PV that a cell commercialized in 82, so 40 years ago, by Kyocera at that time, right now is working at 80% of its initial efficiency 40 years ago. No, it's impressive, I think. So thank you. Is there another question? Okay. If there is no question, I think we are all quite tired, but I think it was a very productive day today, this midterm event. It's the first one we are implementing in the Pillar 1 of LIPRI, but I think it's very interesting and successful. So next will be the second call, midterm event we have to do. Just also some issue, of course, we have, as we said, registered the meeting. The presentation will be on LIPRI website and in the app. I look at Mathilde. But also maybe we will ask you some format for publication. I spoke with Philip Schild and he will be interested for A4 PDF, something like that, but we will provide you the format exact for distribution in a European Commission delegation in Africa, for example, in order to showcase what we have done in LIPRI. So we will come back to you with the format to present that. So thank you very much. Thank you to all participants. Thank you, of course, to the speakers today. So we will come back to you very soon. Mathilde has, I think, some information.
Yes, just a reminder for everyone that the bus departs at 7 p.m. And a second information to please give back your lanyards, the one I don't have actually, so I can show on myself, at the entrance, at the reception desk. You can keep the badge itself, like the paper part, but if you can give us the kind of necklace part, that would be great so that we can reuse for other events and avoid waste.
Does the bus leave from here?
Yes. Yes, and the bus leaves from here, not the Serena.
Recording stopped.